Hello, and welcome to our presentation of Lab 5 by Eric Burns, a software engineering major from Wenatchee, Washington, and Aaron Ike, a software engineering major from Portland, Oregon. We've learned that sequential processing is required to control many of the devices we use today, such as a copy machine. Other examples include a car wash, a dishwasher, or a washing machine, or any device where a given function in a series of sequential functions is reliant upon the outcome, or state, of a previous function. Using the copy machine as an example, the system is designed to wait for a signal indicating the lamp is warmed up before starting the motor to move the scan arm, and to wait for the signal indicating the scan has been completed before turning the lamp off. The key component in the controls of this system is the ability to remember where the system is in the process, so that as signals arrive from parts of the copier, it can react appropriately. In Lab 5, we studied the characteristics and limitations of the simple SR latch, the improved design gated D latch, and finally the master-slave D flip-flop built from two gated D latches. Due to the inherent limitations of the SR latch and gated D latch, only the master-slave D flip-flop can successfully be implemented as a memory storage device in a synchronous sequential circuit design. This is because the master-slave D flip-flop toggles its output once, and only once, each time the gate changes from either high to low or low to high, depending on the design of the flip-flop. In the lab, we explore the functionality of two versions of an SR latch, one using NOR gates and another using NAND gates. As we saw in the lab, the NOR SR latch is asserted when S and R are pushed high. The NAND SR latch is asserted when S and R are pulled low, with the requirement that either S and R are inverted or the routing of their inputs is inverted. Although both can successfully hold a value of 1 or 0, or high or low, in what is referred to as a bistable state, they both present a characteristic which renders them less useful. In the case of the NOR SR latch, this occurs when both S and R are equal to 1, which yields a 0 on both Q and not Q. And in the case of the NAND SR latch, this occurs when both S and R are 0, which yields a 1 on both Q and not Q. Neither of these states are considered useful, so the combinations are usually avoided. Due to the presence of false outputs in the circuits which generate S and R signals, this makes SR latches difficult to use in most sequential system designs. An alternative to the SR latch is the gated D latch, which augments the SR latch by adding two AND gates in front of the SR inputs into the latch, with one gate input being ANDed with each of the S and R inputs. The result provides a mechanism, or gate, that allows input to be turned on or off. In the lab, we explored the functionality of a gated D latch. In this variant, we receive only one input, D, which is inverted in one of the inputs to the AND gate. This has the characteristic that the two latch inputs are always the complement of each other. When the gate is high, or 1, Q output will take on the value of D input. That is, when the gate is high and D is equal to 1, the latch will be set, and when the gate is high and D is equal to 0, the latch will be reset. This configuration not only provides some control as to when the latch can be loaded, it also resolves the problem of both the output and its complement, Q and Q0, being set to 0, by ensuring that the inputs to the SR latch are never both equal to 1. While the gated D latch is useful in certain circumstances, it is not very useful if our goal is to store a value in memory, such as a register. The reason for this is that a gated D latch is an asynchronous device, in that Q follows D whenever the gate is high. In contrast, a flip-flop is a synchronous device, which is necessary if we want to create a globally synchronous solution. As we learn in Chapter 12, this requires that all clock inputs to all flip-flops are tied to the same global clock signal, which ensures that all registers load in unison. To accomplish this, we use two gated D latches together, one referred to as the master and the other as the slave, where the output of the master is fed into the input of the slave, and the gate is inverted on the slave, so that only one gated D latch can load at a time. This is often referred to as an edge-triggered flip-flop, since the output changes only when the gate goes from either 1 to 0, in the case of the falling edge flip-flop, or when the gate goes from 0 to 1, in the case of the rising edge flip-flop. Further, the gate is usually referred to as a clock to signify that it usually rises and falls in a regular, periodic manner. The following transition table shows the expected output of a rising edge-triggered D flip-flop. When the clock goes from 0 to 1, if D is 0, the output will remain at or be reset to 0, and if D is 1, when the clock goes from 0 to 1, the output will either remain at or be set to 1. To demonstrate this, we've built a Latches gate level diagram of a rising edge flip-flop. When the clock is low, the master loads into Q1, whatever D is equal to. Notice that when the clock is low, and we change the value of D to 1, Q1 now equals 1. We say that a master has been loaded. When the clock goes to high, that is on the rising edge, the value of Q1 will be loaded into the slave, and the flip-flop is now said to hold a value of 1. In this instance, when the clock is high, any change to D has no impact on Q output of the flip-flop. Further, if D goes to 0 while the clock is high, the master is not reset until the clock goes to low, and the slave will not be reset until the clock goes from low to high again on the rising edge. This behavior gives us the desired results, a memory device capable of storing either a value of 1 or 0, which changes only on either the rising or falling edge of a clock cycle, thus satisfying the need when creating sequential circuits following a globally synchronous design model. The flip-flop we discussed earlier has only two inputs, a D input and a clock input. The D input can be considered a data input, while the clock input is a control input. Additional inputs can be included in a D flip-flop, including preset, enable, and clear. These controls work as expected, but we would like to emphasize a couple of key points. If the preset is set to high, D has no impact on the output. The same is true for clear. When it is set to high, D has no impact on the output. The enable input, however, has two characteristics. First, it must be set to high for the value or output of the flip-flop to be changed by D. Second, and possibly more important, when enable goes low, whatever value was stored in the D flip-flop will be retained. Finally, if preset and clear are both set to high, the clear will have priority and the D flip-flop will hold an output value of 0. Lab 5 also includes the design and logicism of a toggle circuit, which demonstrates how the output only changes on the rising edge of the clock. Notice how in the diagram, as the clock cycles high and low, Q is only changed on the rising edge of the clock, or when the clock goes from low to high. In a perfect world, when one pushes a switch button, the electrical contact would be immediate and perfect, completing a circuit and allowing current to flow through. Unfortunately, switches do not behave this way in the real world. When you push down a switch button, the electrical conductor may contact and break contact several times momentarily while it's being physically connected to the positions it's trying to conduct. This is called switch bounce, because the behavior we see in the signal bounces up and down. Imagine trying to write a timing diagram against this. There are several ways to resolve this problem, and it is commonly referred to as debouncing. One hardware solution to switch bounce is the introduction of a flip-flop, a pair of cross-coupled NOR gates. This produces a rising or falling edge that can be reliably detected as the relevant switch signal. The final task of this lab was to research and become familiar with specification sheets, or data sheets, that give us the various delays inherent in different circuits. These specifications may include propagation delay, setup time, hold time, guaranteed frequency. The key takeaway from this portion of the lab was to understand that different components have different limitations and boundaries within which they can operate correctly in digital circuits, and it's important to be aware of the limitations of a given circuit when designing real-world applications.